Now the place where angular momentum matters most is in magnetism. As the electron orbits around a nucleus, if it's got some angular momentum, it will have a magnetic dipole moment. And the link between those is that the magnetic dipole moment is equal to minus the electric charge E over twice the mass of the electron times the angular momentum. The minus sign just becomes because the electron is a negative charge. Well, we know that the angular momentum is quantized, and in fact the total angular momentum follows this pattern. The angular momentum of a particular electron in a particular orbital is just the square root of the orbital quantum number L times the orbital quantum number plus 1 times h bar to give it the units of angular momentum. If we put that together with this relationship for the magnetic dipole moment, we get this relationship that says the total magnetic dipole moment of an electron from its orbit is just E over 2m times the square root of L plus 1 times h bar. But we never know the exact direction of this. We cannot measure all three components of angular momentum in quantum mechanics. There's always some uncertainty. What we can do is measure the component along one direction. And if this magnetic dipole moment is interacting with a magnetic field, then the energy really just depends on the dot product of that magnetic dipole moment and the magnetic field, which means it's just the component of the dipole moment along the magnetic field times the magnetic field. So the magnetic field itself defines the direction of our z-axis. In that case, what we really want to know is what is the component of angular momentum along the z-axis? Well, that's just the magnetic quantum number, ml, times h bar, which means the component of the magnetic field, or excuse me, magnetic dipole moment along the axis is just minus ml times what's called the Bohr magneton, which is just a convenient way of putting together this E over 2m and the h bar. So it's E h bar over 2m. That's the Bohr magneton. And this is its value right here. 9 times 10 to the negative 24 joules per Tesla. Okay, I'm going to move these over here for a bit, because I want to bring up this picture right here. What this picture shows is the angular momentum vector, quantum mechanically, and its projection onto a z-axis, where the z-axis is defined by the direction of a magnetic field. Notice for a single value of the total angular momentum, this is a orbital quantum number L equals 2 situation. So 2 times 2 plus 1, which is 3, that's the square root of 6 h bar. That's our total angular momentum. But I can have a component along the z direction anywhere from 2h bar up to negative 2h bar down, and that includes h bar 0 and negative h bar in between. Sometimes it's convenient to define this angle here between the z-axis and the orbital angular momentum. That angle has a cosine equal to Lz over L, which is just m sub L over the square root of L plus 1. Now, technically, we cannot measure the exact direction of this vector. We only know it's on a cone swept out around the z-axis. And for that reason, because we can't really exactly measure this angle, it's known as a semi-classical angle. But it still can be useful.